Okay, welcome everybody. We're going to be looking at free response questions for Unit 4 today in our progress checks. And so question number 1 is a long version free response question. And your free responses usually get like 2 long ones and 3 short ones. And so let's go ahead and see what this one entails. So it reads, students conduct an experiment studying the motion of 2 rockets. In the first experiment, rocket X has a mass mr, and is launched vertically with an initial speed of v0 at time t equals 0. The rocket continues upward until it reaches a maximum height at time t1. As the rocket travels upwards, frictional forces are considered to be negligible. The rocket then descends vertically until it reaches the ground at time t2. The figure above shows the toy rocket at different times in its flights. In a second experiment, which has not yet been conducted by students, rocket Y of mass big MR, where big MR is larger than little MR, will be launched vertically with an initial speed of V0, which is the same as before at time t equals 0, until it reaches its maximum height. Rocket Y will then descend vertically downward until it reaches the ground. And so 2 students in the group make predictions about the motion of rocket Y compared to that of rocket X, and their arguments are as follows. Rocket Y will have a smaller vertical displacement than rocket X. Although it is launched upwards with the same speed as rocket X, it has more kinetic energy than X because rocket Y will have a smaller maximum vertical displacement than rocket X, and so this is the next part. I predict that it will take less time for rocket Y to reach the ground compared to rocket X. Student 2 here says, rocket Y will have the same vertical displacement as rocket X because both rockets have the same kinetic energy. Since both rockets have the same vertical displacement, I predict that it will take both rockets, the same amount of time to reach the ground. And so for the first part here, we have to decide. For part A, ignore whether the student's predictions are actually correct or incorrect. So don't worry about that right now. And do not simply repeat the student's arguments as your answers, okay? What they want you to do for part A, section 1 is for which aspects of student 1's reasoning, and so I'll go ahead and change the screen real quick. If any, which aspects of student 1's reasonings are correct and explain your answer. So for this one here, do you guys want to take some time trying to answer it on your own, or do you want me to just kind of go ahead and talk about the explanation or the answer? Let me know in the chat. Okay, alrighty. So we have like 5 minutes for us to think in our heads. So this one's supposed to be about 25 minutes, and there's 1, 2, 3, 4, 5, 6, 7, 8 questions. So if anything, maybe like 3 minutes. So I'll give you guys maybe about a minute or 2 here to think about it in your heads. And right now we have to determine which aspects of student 1 reasoning, if any, are correct. And more people are asking to be given some time to contemplate. In the meantime, I'll go ahead and copy over the College Board scoring guideline so that y'all can see what they were looking for in this question in terms of answers. Alrighty. Hopefully you feel like you had enough time to think about this one. And we can go ahead and say that, well, the student is correct in saying so we're only looking at assertion. So they are saying that the speed they're launching both rockets with the same speed. So I'm going to say that student one is correct in saying they are correct in saying both rockets are launched with the same speed. So that's one thing they did say correctly. They told us this, that the initial speed is v naught and the initial speed is v naught as well. So, okay, I would agree with that. Now, if we remember, they said something about kinetic energy, and kinetic energy is 1/2 mv squared. And student one said that it rocket Y will have more kinetic energy than rocket X.
Mr. Gusk, are you writing on?
Oh, shoot. Yes, I forgot I had paused the screen share. Thank you. Okay, thank you. Yeah, I didn't see, I had hit the menu on top of that, so I didn't see the things coming up in the chat. I'm sorry. So if we look at this, they're telling us that rocket X and Y have the same initial speed, but rocket Y has a larger mass. So they are also correct. And they are also correct. Also correct about rocket Y having more kinetic energy. Okay. And so let's see here if they say anything else, because rocket Y will have a smaller. So plot twist, hopefully we remember that if we launch two objects with the same speed, and if we ignore friction, both objects will go to the same height. So them saying that rocket Y will have a smaller vertical displacement than X is not correct. And then we also ignore, let's see here, and ignore whether the student's predictions are correct or incorrect. So we won't worry about this other part at the end, that it will take less time for Y to reach the ground compared to rocket X. Any questions? And if not, we'll go ahead and type them in the chat. I have the menu open, but we're going to go ahead and look at section 2 now. Which aspects of student one's reasoning, if any, are incorrect? And then I think we have to explain our answers. Since kinetic energy depends on the mass, and rocket Y has a larger mass. X. Okay. And the same speed, just in case. So I'm going to go ahead and paste here what the College Board was kind of looking at here. Let me move to the select tool. Let me click on this. That'll push this guy down, and let me go ahead and paste this feature here. And so they were saying, okay, student one is correct that rocket Y is launched with the same speed as rocket X, and since rocket Y has a larger mass than rocket X, rocket Y has more kinetic energy than rocket X, and that's it. Okay, let's go ahead and look at the next one. Which aspects of student one's reasoning, if any, are incorrect? So let's go ahead and see here in plot twist. I think I already gave you one of them. I'll let you guys think about that. Let me see the chat here. Very good. Straight up the College Board answer. Very nice. Right on the money there. And let me go ahead, and while you guys are thinking about that one, let me go ahead and copy over their example response. So in this case, when we're trying to figure out, well, what is incorrect? The student one is incorrect in that rocket Y will have a smaller vertical displacement. The student is incorrect. That one is incorrect in stating that rocket Y will have a smaller vertical displacement. Aspect. Go here. Displacement. Where's my pen? Okay. And why is that? Well, if we look at it, both rockets have the same initial speed. Initial speed. And the same acceleration. It's the acceleration due to gravity. Gravity. So they will experience the same vertical displacement. They're both going to take the same amount of time to lose their speed, and if they have the same velocity and they lose it at the same rate, they're going to climb to the same height. The way the College Board puts it, and let me go ahead and push this down and go ahead and paste their answer. Student 1 is incorrect in saying that rocket Y will travel a smaller vertical displacement than rocket X. Both rockets have the same initial velocity and same acceleration, therefore they will reach the same maximum vertical displacement. The mass of the rocket does not affect the vertical displacement. If we look at this, yes, it has more gravitational force pulling it down because it's m times g. But if the force due to gravity is the only force acting on these on the way down, well, then the force due to gravity is the net force, and we can go ahead and set that equal to m times a. And so this is the inertial mass, this is the gravitational mass. Experimentally, they have been shown to be the same value, so mathematically they cancel out, and the acceleration they both experience is the same if there is no gravitation, no frictional forces. Let's go to number 3 here. Section 3 of part A reads, which aspect of student 2's reasoning, if any, are correct? And we'll explain your answer. So student 2 says, rocket Y will have the same vertical displacement as rocket X because both rockets have the same kinetic energy. Since both rockets have the same vertical displacement, I predict it will take both rockets the same amount of time to reach the ground. I'll let you guys think about that here. I'll keep showing it and then we'll see what the College Board is looking for. Sorry, I don't know how well this, and we only need the blue one here. How well this shows up on your screen, but if you have a small screen, I do apologize. Let me check the chat. Oh, what about what student 1 said about the time? So really important, if we look at this part here, they say ignore whether the student's predictions are correct or incorrect. So when they say, I predict that the time will be less or whatever, you ignore that part. So thank you for asking, because yeah, that's the big part there, that why I didn't talk about it. So because he says, I predict that it will take less time for rocket Y to reach the ground compared to rocket X, we don't analyze whether or not that is correct. He is definitely wrong on that. But because they tell us to ignore the predictions, we just won't like add it as part of our analysis. Okay. All righty. So let's see here. So here, student 2 is correct about the vertical displacement of the rocket. And technically, he is correct about the time it will take both rockets to hit the ground. But again, we're not going to worry about the prediction. Okay. So we're going to say here that student 2 is correct in saying student 2, whoa, let's change the color of that. Student 2 is correct by saying, whoa, my pen is waking up. There we go. Saying that both rockets have the same vertical displacement. Since they have the same initial velocity and acceleration during their motion or during their ascent. Any questions on this one? And again, we're going to ignore the prediction about time because they told us to do so. And I don't think they would penalize you if you mentioned that, but they're going to be kind of like, you didn't read what we asked of you. But it's whatever. I wouldn't stress over it. But it's important, especially here where time is of the essence. Only answer the question, or look at the question and answer it specifically. Don't give them more. Don't give them less. Just the right amount. Okay. So let me go ahead and let's see here. Oops. Bring this bad boy. Let's make some space. Space created. And let's try pasting this here. So student 2 is correct that both rockets will have the same vertical displacement because both rockets have the same vertical velocity and the same vertical acceleration. And the mass of the rocket does not affect the vertical displacement. So here, I wonder if I would have lost points. Let's see here. Yeah, because I didn't say the same vertical velocity. If I were like a super stern AP grader, I would be like, well, in which direction? I'm not going to give you the point because you didn't say the direction for velocity and acceleration. So vertical. I think we all understand that these things are moving vertically. Well, whatever. But yeah, definitely be specific. All right, let's go ahead and see here. Which aspects of student 2's reasoning are incorrect now? So we're looking at the blue statement and seeing, well, what is incorrect? I'll give you guys a little bit of time here to ruminate on this one. For these parts here, I would say you should do these quicker, like just where you have to determine what's correct and what's not. Because in a bit, we're gonna have to create equations. And that's where we kind of want to spend our time on. Make sure my filter's up. My room's still a mess. All righty. So if we look at this, the main incorrect statement here is that they have the same kinetic energy. Exactly. Rocket Y has a greater mass, so the two rockets do not have the same kinetic energy. Very good. So both rockets
do not, or that kind of sounds bad, starting out with both. We could say while both rockets have the same initial, both rockets have the same initial vertical velocity. And rocket Y has more mass, it will have a larger kinetic energy. Than rockets. Okay. And if we want to, we can go ahead and get the reasoning here that they're looking for in this section. And we can go ahead and see here. Oops, Control Shift S. The College Board's explanation. And let me shrink that a little bit. So student 2 is incorrect in saying that the two rockets have the same kinetic energy. Even though the two rockets have the same initial vertical velocity, they have different masses, so they have different kinetic energies. All right. Use quantitative reasoning. What that means is that you can explain things by numbers. And so you're going to use the relations of variables to derive expressions for the maximum heights achieved by rocket X and rocket Y. And we're going to express our terms in our answer. Oh, you have to specify that it is initial kinetic energy. We probably should have a larger kinetic at the beginning. Yeah, I think we definitely want to be specific because they could play a devil's advocate. It's like, does it always have a larger kinetic energy? And I would say yes, technically, until the very last second when they lose all their velocity, at which point then they both have the same kinetic energy of 0. But yeah, it's good to be specific here. All right, so I'll let you guys think about this one here for a second. And your answer should be in terms of V original, the mass of rocket X, which is little mr, the mass of rocket Y, which is big mr, and then G and any other fundamental constants as appropriate. And we'll talk about fundamental constants here again in a bit. Let me go ahead and copy their response. And since we are dealing with energy here, we should be thinking, okay, how can I approach this through energy? They keep talking about kinetic energy and this vertical displacement height. And so we should be thinking, oh, you know what? I think that that gravitational potential energy it has at the end, or the rockets have at the end, came from their initial kinetic energy. So because friction here is negligible, the energy in the rocket Earth system is going to be conserved. So we can go ahead and say that the kinetic energy of the rocket will become gravitational potential energy. We could put a little O here for the original kinetic energy, will become the final gravitational potential energy of the rocket Earth system. And so we could say, well, that's 1 mv squared over 2, 1/2 mv squared equals mgh. Now here, we can go ahead and have our answers show up with these variables. So let's go ahead and now substitute them. This is the general expression or formula for these two terms, but we can go ahead and say, okay, well, the mass of rocket X, which is little mr, times its original velocity squared over 2 is going to be equal to, well, that's the mass of the little rocket, so it's little mr, times g times h, the height that these guys will go to. We could even call this delta y. The height of that these rockets go is really the vertical displacement. Now here, they don't tell us what variable we can use for the heights. So you could either leave it as h or delta y. And I'm going to go ahead and just kind of leave it as h here. So I'll go ahead and erase this to avoid any clutter. When we start to move this over, we divide by and little mr and g. We can do that in one fell swoop. And we're going to do that over here. And so this expression, and I'm going to go ahead and create some more space here so I can work. This expression here can look a little messy, but it becomes little mr times v original squared. And we're already dividing by 2, and we're trying to divide this quantity into that, so we get 2 little mr. So I'm going to do this for the little rocket first, and then we'll go ahead and do it for the big rocket. Can we use T1 in the equation, or should we use only the variables in the list? Because I was thinking we can do that. So what we have to do is we can go ahead and use Newton's laws of motion, Newton's second law, to prove they have the same acceleration, and then you could use the kinematic equations. The big thing here, though, is how do you immediately know to go? So, and so I'll answer the previous question real quick. So we could use T1. The thing is, we don't know. I mean, we should know that it's the same height and the same amount of time. But because we're trying to prove that they reach the same height, which will yield the same amount of time to rise, you kind of catch yourself in this like chicken and the egg scenario if you do it through kinematics. We can prove that the acceleration is the acceleration due to gravity, and they both have the same vertical velocity. Then you could use the velocity equation to get the time for both of them and prove that T1 for both rockets is the same. Then you could go to get the height. So you could do it through kinematics. It's just more steps.
Mr.
Yeah,
Gus, but the only thing is, if we do it through kinematics, would we still be able to use all those same variables like mass?
So the masses will cancel out, and that won't matter. But they, like they said here, they didn't want you to use T1 or the acceleration per se, just G. And so you can kind of like get dock points for that. So in this case, go ahead.
Or whenever they put like, make sure like express your answer in terms of this, this, and this, like that doesn't mean that it has to be in your final answer. Or?
Correct. But you can't just leave other variables in there either.
You have
So
to
it's
show
fine.
your
I'm sorry, go ahead.
You have to show your process using those variables.
Yeah.
Okay.
So it's okay if V, little m, big M, and G are there, but it is not okay if you have some other variable in there. You would need to use some kind of equation to substitute and get rid of the extra variable, which is kind of the issue with the kinematics approach. You would need to prove that the time is the same for both of them and somehow cancel that out, which you wouldn't be able to. But you could do it through the v squared equation, because usually the v squared equation, doesn't have time, and we can circumvent it that way. So let me finish this one here, and then we'll do the other ways, just so that you can see how we could do it. Now, the other question, how did I immediately know to go to K equals U? Well, part of that is experience. In reality, we are doing energy conservation, which means that the original energy of the system equals the final energy of the system. And you can take inventory. That's going to be some kinetic energy at the beginning, maybe some gravitational potential energy at the end, maybe some spring potential energy at the end. And all of that will be equal to some kinetic energy at the beginning. So, and all of this quantity will be equal to maybe some kinetic energy at the end, plus maybe some gravitational potential energy at the end, plus maybe some spring potential energy at the end. So this is kind of what the energy conservation equation would look like in a more general case. But because we don't have springs, we don't have to worry about spring potential energy here. At the beginning, we ask ourselves, well, what kind of energy did this rocket have? Well, it did have kinetic energy. It was moving, but it started on the ground, and we can measure the height to be 0 at the ground and say that is where we have 0 potential energy. And then once it's at the peak of its motion, we ask ourselves, well, does it have kinetic energy? And well, because it's at its peak, it needed to have stopped momentarily. So this quantity is 0. And so then we say, well, it does have some height now that it's up there. So this object will definitely have gravitational potential energy. So this would be the long way to know that the kinetic energy becomes potential energy. But it's one of those that through experience, I just kind of think about it. Okay, well, energy is conserved. And what do I have at the beginning? Just kinetic. What do I have at the peak? Just potential. Let me just set those two quantities equal to each other. And so I just know that immediately, partly through experience and by just looking at this equation very quickly, or just asking myself, what kind of energies do we have at the beginning and at the end? I don't know if that helped or answered your question. I basically asked myself, does it have height? Does it have speed? And if it's yes, then it has kinetic or gravitational potential. All right, you have to go somewhere? No problem. Have a good evening. Thank you for stopping by. Oh, come on, Red. Let me pause or let me minimize OneNote real quick. It needed to sync up. And what we find out is that the height here is going to be given by V original squared given to G. And we could even make a note here just to kind of save ourselves some work. Let's go from lilac to something a little darker. Ooh, violet. Okay, we could say, no, that's not enough value contrast. That's too dark. We'll go with this. Since mass cancels out, the height of rocket X will be the same rocket Y. So we could actually do another calculation here. And we could do it with big M. And let me go ahead and just make some space here. No, not there. That's beneath. Other questions so far? This will be the same as rocket Y. Okay. So this is the energy approach. And just recognizing that they were talking about energy, we should have done maybe this calculation, the conservation of energy. Now let's go ahead and look at it through forces and kinematics. So dynamics, kinematics. So this approach here was energy conservation. And then now we're going to be looking at the forces and the kinematics. So if we look at this situation for these rockets, we're going to assume that they are point masses. And if we look at the forces acting on them, these guys were shot up. Something forced them up, giving them an initial velocity. But while they are in the air, the only force they experience is the force due to gravity. Please change to green. Let me minimize it one more time. Hopefully that fixes our issue. We'll be stuck with green for the remainder of the day. Please. One more time. quote a famous defunct music group. So if we look at the forces on these rockets, we're going to ignore friction and air resistance. And the only force while they are coasting on the way up to their maximum peak is the force due to gravity. So when we do Newton's second law, M times A, we say, well, the force due to gravity equals the net force. And the force due to gravity is given by M times G equals A. We can say that the, oops, I forgot M here. Let me know if we have any questions in the meantime. And we could be specific. We could say, well, this is little m of the rocket. And we could do this calculation again for the big rocket or the big mass. But regardless, the masses cancel. And we say that the acceleration here is g. Now, we can go ahead and think, okay, well, if I'm going to do this through kinematics, I don't want to introduce any more variables than I have to. So if we remember, time is not allowed in our answers. So we're going to use the v squared equation to get an expression for the height that does not depend on the time. And so here we recognize, well, both rockets, the final velocity will be 0 at their peak. The original velocity is just VO. The acceleration is that of g. And technically, we say that, because it's moving this way, this will be positive. So we need to define a coordinate system in this case, which makes this technically negative, and I got sloppy there. The acceleration is negative g. So when we solve for this, we get v final squared minus v original squared equals 2 times a times delta x. My a got a little derpy there. And then we can go ahead and solve for the displacement and say that the displacement will be the final velocity squared minus the original velocity squared all over 2 times the acceleration. And we can make a substitution for the acceleration. We get 0 minus the original velocity squared, whilst when we substitute for the velocity at the end, minus g. And we get the same thing. Oh, and I lost a 2. We get the same expression here, v naught squared all over 2g, because the negatives cancel. So we would get the same expression whether we did it with the v squared equation or with the energy conservation, and the masses cancel out. And this would be the quick and clever way to answer this question if you're using forces and kinematics. Because otherwise you would need to get t as 0 minus v original all over a, and then you're going to take a really negative g. And you're wondering, how did I get this quickly? Well, I remember the final velocity is the original velocity plus the acceleration times the time. And this is going to be 0. I move this over through subtraction, and I move this over by division. And we get the time is v naught over g. And then let me go ahead and scroll over. And you could call this T1, but they don't want T1 in our answer. So then now when we go to delta x equals v naught t plus 1/2 a t squared plot twist, we're going to get the same thing. We get delta x equals v naught times v naught over g plus 1/2 of negative g, and then t squared is going to be v naught over g quantity squared. And I need to make a little more space here. And we got, let's clean this up. Delta x is v naught squared over g plus, or sorry, really a minus. Let's see here. This g here is going to get a little funky. We're going to put a minus g over 2. I'm going to combine these guys right here. Then I'm going to square the stuff in parentheses. V naught squared over g squared. That's going to cancel one of these guys. And so we get delta x equals v naught squared over g minus v naught squared over 2g. And we're wondering, how do we clean this up? Well, I have a whole minus a half. In reality, that means I have a half. I get v naught squared all over 2g after we combine and we get common denominators. So we still get the same thing regardless of the equations that we use. We just have to be very careful about our substitutions. And the reason why people really like energy conservation is if things are nice, that lets you save a lot of time in your calculations. Any questions? So for the person asking about 1/2 AT squared, you could have done that, but then you'd have to replace T because they didn't want that in their answer. There's more than one way to skin a cat. Okay. So let's go ahead and continue. Using quantitative reasoning, including equations as needed, derive expressions for the time it takes the rocket X and rocket Y to reach the ground after reaching their respective maximum heights hx and hy. Express your terms your answer in terms of v naught, little mr, big mr, hx, hy, and g, and other fundamental constants. I'll let you guys think about this. Let me make a little more space. Oops. Let's see here, what expressions come to mind or equations come to mind. And I'm going to paste the scoring guideline too. Oh, maybe that's a big one. Let me scroll this a little further down. And so for the person asking about kinematics, sorry, I'm trying to keep things anonymous for the sake of the recording. If you look at their note, these points can also be given for deriving an expression through using kinematic equations. In that case, the first point would be given for use of an appropriate kinematic equation that can be used to solve for the maximum height of the rocket. And the second point is given for the correct equation for the maximum height of the rocket. And that's where we would have needed to have made the correct substitution so that at the very end we get v naught squared over 2g. So let's continue focusing on C. Oh wait, I need to resume share, sorry. Yeah, I was talking about here in part B, how you could use kinematics. You just needed to make the appropriate substitutions so that at the very end, your equation looks something like this. They happen to use Y final for their height. They didn't tell us what they wanted for their as a variable for height. I just called it H. Okay, I'll let you guys think about this one a little bit more, and then we'll go ahead and jump into it. And let me make a little more space. Any questions so far? Okay, let me go ahead and just try to draw a little bit of a ground. That's a little too dark. Let's use a lighter brown. That might be the same value. But, that's pretty good. So we have our rocket, which is going to be modeled as a point mass with some velocity equal to 0. It is some height above the ground. Use the arrow for this, shapes. All right. So here we're going to need to find the time it takes it to drop. So it's going to start out at some original vertical position, and then it's going to end up with some final position YF equal to 0. So if we look at this, we're trying to find time. We know the original velocity is 0, and we know positions. Oh, and we know that the acceleration acting on them downward is equal to the acceleration due to gravity. So we're going to go ahead and say that up is positive, down is negative. So if we look at our equation for kinematics, we can say delta y is v original in the y direction times time plus 1/2 the acceleration in the y direction times time squared. And this original this original height is either going to be hx or hy, but we'll make that substitution later. If we look at this, delta y will be y final minus y original, which we can say is going to be 0 minus y original, where y original can either be hx or hy. We will make this substitution later. For now, I'm just going to say that the displacement here is just negative y original, the original vertical position of these rockets. Okay, so recognizing that these rockets are going to fall from their peak from rest. Oh, come on, man. Give me 1 second. I'm going to close OneNote and hopefully that fixes things. I don't know why it's so hiccupy today. Let me go back to the screen share. Let me enable it. Screen share OneNote. Okay. So because the original velocities for both rockets are going to be 0, that will cancel out. And our expression starts to become delta y equals 1/2 the acceleration in the y direction times time squared. And so our acceleration in the y direction is going to be negative g, if you will. They want us to use g, not the acceleration due to gravity. You could say a sub g or g, but generally we just say g. Okay, gg. So we get 2 times delta y. We move over the 1/2 through multiplication because we're dividing originally. And then we divide by the vertical acceleration, ay equals t squared. Or we can go ahead and say t is given by the square root of 2 times the vertical displacement over the vertical acceleration. Now we can go ahead and say the time for rocket X to return is going to be 2, and it's going to be a negative here. So we have to be careful. It's going to be negative hx. And we may be thinking, but Mr. Gasco, like, we can't take square roots of negatives. And I'm like, well, you know, you can do complex numbers, but we're not going to worry about that here because we're going to get a real value if we make our substitutions correctly. Because vertical position was measured positive to be up and the acceleration is down, this is going to give us a negative g for our acceleration. And what we get is this time for x to fall is going to be given by 2 times the height of object x all over g. Give me 1 second. Let me let's guy over. All right. And we can get the time for rocket Y to return. And let me use a capital Y because they use a capital Y. It's going to be given by the square root of 2 times a negative hy all over negative g. And the negatives are going to cancel. And we get that it is given by square root of 2hy all over g. Oh, well, here are the times for each of the rockets to drop from their respective heights. And it is given by the square root of their height times 2 all over g. Let me know if you have any questions. Okay, looks like we have no questions. If we want to, we can look at their the College Board solution. And so here's their idea. So the alternative solution is to find the time it takes it to reach the ground, or by getting the final velocity upon hitting the ground, and then you substitute that time for that final velocity into the equation, and then you manipulate everything over. Actually, you could just say, well, it's going to gain whatever velocity it had going up, but this is what we did here, the example response. Okay. Go ahead and look at the last two questions here. Explain how any correct aspects of the student's rationale identified in part A are expressed in your mathematical relationships for part B. So in part B, we were talking about the maximum heights and the times. So we could say that, so let's go ahead and I guess break it down by student 1 and then student 2. Push it down. So student 1, what did student 1 already say? And so I already forgot. Smaller vertical displacement, same speed, more kinetic energy. It will have, I predict that it will take less time. So of each student's reasoning, identify in part A. So I don't think they really said anything here correct that matches our mathematics. Yeah, we could just say that they were incorrect about the vertical displacement. They had the same speed. So let's see here how the College Board actually wanted you to answer this, because it kind of, yeah, this is just, really it's just a rocket Y that is correct, or the student talking about rocket Y. So for this scenario, they say because rocket Y had a greater mass than rocket X, both objects are launched with the same initial speed, and K equals 1/2 mv squared. Rocket Y has more kinetic energy than rocket X. However, when conservation of energy is applied to the rocket or system, the masses cancel, meaning the masses for the rockets do not affect the final height that is reached by the rocket. And so, yeah, this one is just basically talking about, okay, setting the kinetic energies, recognizing the kinetic energies are larger for rocket Y than for a rocket X, but then because the masses cancel, they attain the same height. For C, which is talking about the time specifically, since, where am I going to go? I guess here we could say, since the times depend on the height, the maximum height they fell through, and the acceleration due to gravity, due to gravity. I didn't analyze student 2 and make the assertion, but yeah, student 2 was the one talking about kinetic energy here. And the acceleration due to gravity, both rockets will take the same amount of time. So I think what student 2 was saying, yeah, it will take both rockets to the same amount of time. And so we can look at what they were saying. And so here we're just kind of looking at the math for the equation that we got. And so because both rockets will experience the same acceleration, and because both rockets reach the same height, they will take the same amount of time to reach the ground. All right, so that's question number 1. Question number 2 is going to be a little bit faster. It's only 3 main questions. Wait, let me make sure. It's probably two main questions and then like a subpart for one of them. Yeah, okay. All right. So let's go ahead and zoom in on this one. And then we'll go ahead and see here. So we have a person that is jumping off of a platform and they happen to have a cord, probably an elastic cord or a bungee cord attached to them. And so they're going to come down and they're going to stretch the cord and they're going to come to a stop once the cord has been stretched. And it reads, an amusement park ride is designed such that one end of an elastic cord is fixed to a platform that is a distance d above the ground. So let's go ahead and start highlighting some of our main information. The other end of the cord is attached to a person of mass m, and the cord has an unstretched length of L. To begin the ride, the person jumps up from the platform with an initial speed v original as shown in figure 1. As the person falls, the elastic cord stretches and can be modeled much like a spring of negligible mass. After the cord can no longer be stretched, once it has reached maximum extension, the person is a distance h above the ground and is no longer in motion, as shown in figure 2. And then they tell us the reference position for zero gravitational potential energy of the person cord Earth system is a distance h above the ground, and all frictional forces are considered to be negligible. Well, the first part here is the initial state of the system is shown in figure 1 and the final state of the system is shown in figure 2. Describe the energy transformations that take place from the initial state to the final state of the system. For each form of energy, identify the object or system that has that form of energy. So we should think, what kind of energies do they have at the beginning? What kind of energies do they have at the end? I'll let you guys think about it for a second. And this is kind of like what I do, and I know right away what kind of energies we're going to have. Oh, shoot, I brought a little carbonated water and I never drank it. 1 second, my throat is a little parched. Stay hydrated, homies. Yeah, it's just water, like whatever. But it's flavored, it's tasty. All righty. Another sip. One of my whiskers, that's good stuff. To quote a Dota 2 character. All righty. So in the initial state, well, what kind of energy is this pump going to have? Well, they have some height above the lowest reference point. And they have some initial velocity. So we can say in the initial state, the student has kinetic energy we could also say that the student Earth system, and so we have to get really technical here. Remember, an object by itself does not have potential energy. It's a system. And so the student Earth system has gravitational energy. And because the cord is not stretched, we have not stored any potential energy in the cord student system. There is no elastic energy being stored yet. And so that's what we have at the beginning. And all of that energy, that kinetic and gravitational potential energy, is going to be conserved and transformed such that at the final state, in the final state, the student no longer has kinetic energy and the Earth student system no longer has gravitational potential energy as they have been formed. We have stretched this spring. We are at the lowest point in our path. We have no gravitational potential energy. The student is no longer in motion. So there is no kinetic energy. Well, where did all that energy go? Well, it was transformed into elastic potential energy in the student chord, we'll say of the into elastic potential energy of the student chord system. I think, let's see what the College Board says. I think they just say the chord, but again, for potential energies, you should be considering two objects. Okay. Okay, no. I have the wrong one. Let's go ahead and see here. Okay, no, yeah. Oh, they even include the Earth as part of the system for the chord. I guess. I don't think that's that important. But let's see here. At the beginning, the person has kinetic energy because the person has velocity. Ooh, did we need to state why? No. Okay. So the parenthetical statement of because they have velocity doesn't matter. Okay, no problem. Have a good one. I know we're kind of running a little late. We'll be able to finish this one pretty quickly. The person chord Earth system has gravitational potential energy and kinetic energy. So here they're already just calling the whole system that. And then at the end, we just have spring potential energy. And they say that the person has no mechanical energy. That's because this is kind of like a contradictory statement, or it can be a little confusing here. They say the person themselves has no mechanical energy, but that's because the person chord Earth system has the potential of the mechanical energy in the form of spring potential. No problem. Have a good one. So I think we would get by on this. But if you just kind of wanted to define your entire system here, then you could go ahead and say that, like the way they did. Okay, now for the equation. Derive an expression for the spring constant of the chord in terms of D. Oops, I thought I had my highlighter. D, L, H, V, naught, and M. Okay, so if we have the person chord Earth first chord system, we're going to start out with some kinetic energy at the beginning, some gravitational potential energy, and the spring potential energy at the beginning is 0. And all of that is going to become, well, there's no kinetic energy at the end, no gravitational potential energy at the end, but there is going to be the spring potential energy at the end. So we can say the original kinetic energy and the original gravitational potential energy become spring potential energy at the end. So that's 1/2 mv squared plus mgh equals 1/2 k times delta x. This is the stretch length of the spring squared. So we're going to have to be careful because we're going to have to make substitutions here for all of these quantities? Well, we can go ahead and say, well, okay, we're allowed this part, we're allowed the mass, we're allowed the acceleration due to gravity, that's a physical constant. The tricky thing here is we have to be careful with H, E, and L. Let's go ahead and see here what these mean, because the stretch of the spring or the cord is going to depend on these variables, and so will the initial height. So they're telling us that H is going to be the height above the ground. And that's kind of annoying because if you notice here, they're using a lowercase h. But what they really mean is this big H here. So I think they kind of lost track of their variables because nowhere else do they define H in this scenario. They tell us that D, oops, this looks messy. Let's just erase that. When I said H, I defined H to be from the ground all the way up. But we have to be careful here. They are telling us that we are going to be setting gravitational potential energy at some height. So this is where we're going to measure our height from. That's why I had it off the ground. We're going to measure the height that the person starts out with from that distance, capital H. So if we look at this, lowercase h, h for mgh here is going to be the total distance d minus capital H here. And let me know if we have a question about that. Why is there no gravitational spring energy in the beginning? Very important. So there is gravitational potential energy, but there is no spring potential energy because we have not stretched it. It's only when we actually stretch the cord that we store energy in the form of spring potential energy. So U just means potential, and US means spring potential energy. And that is different than UG. This would be gravitational potential energy. And the reason why there is no spring potential energy at the beginning is because the cord is not stretched. Whenever we write this delta X here, delta X is the stretch length. The length, the amount of stretch or compression. So let me know if that answers your question or if you have a follow-up. Okay. So let's go ahead and see here. So in this case, the original height of our person is going to be D, the height of that platform, the distance to the top, minus this variable H, where we are going to come to a stop, and they define the gravitational potential energy to be 0 here. So we measure from that point. So we got this one taken care of. The next thing is we need to ask ourselves, well, how much did the cord stretch? Well, they tell us that the unstretched length, this is the original, let me make sure here, because I think I'm making an assumption. Yeah, big L is the original unstretched length. Unstretched length. Okay. So normally, let's just try to visualize it. They don't tell us how long that is, but it's going to be shorter than the full stretch of the cord. So let's say this is the original length of the cord, if I were just to let it hang from the bottom of the platform. Now from here, it's going to stretch this much. Which if we look at this, we can calculate the displacement the displacement of this is going to be the total. So delta x is going to be the final length minus the original length. The final length of the cord is this entire purple line here. That entire purple line was already called d minus h. So here we're going to have d minus h. And then the original length is just going to be L. So now we have how much the spring or the cord has stretched. It is the final length, which is this purple line, minus and let me go ahead and give it another color, minus this original length, which is this orange line. So the original length of the cord could be thought of as L, and we're only concerned with how much we stretch it from that point. And so that if we take the total distance and we take away the height from the bottom of the ground to where we stop, that'll give us how much its final length was. And then we take away the original length to find out how much it stretched from there, which would be this purple bit. So we can go ahead and say delta x. Let me write that in purple. This one's kind of like the nasty one. D minus H minus LO. Okay, so then let's go ahead and do some algebra. We move over the 2 by multiplying by 2. That cancels this. We move the 2 over. Be careful, you're going to have to distribute that monster. And we start to get mv naught squared plus 2mg. And then h here, we're going to have to make a substitution. D minus h equals k times, and then we're going to make the substitution for delta x. I'm going to use brackets. D minus h minus L. Sorry, not LO. They want us to use L. And all that monster gets squared. So we can go ahead and divide through by the stuff in the brackets, and we get k is given by mv naught squared plus 2mg d minus h all over the monster in the brackets squared. D minus h minus L squared. And so there's our answer for that one. Let me know if we have any questions. If we look, we've used all the variables. They just fumbled, or I don't want to say they fumbled, but they should have put a capital H there for that one. All right, let's go to the last question and let's see here. Suppose that air resistance cannot be ignored. For the position at which the person has jumped from the platform and the cord reaches its maximum stretch length, how does the stretch length of the cord in the case with air resistance compare with the stretch length in the case in which air resistance is ignored? Briefly state your reasoning. So if friction is not negligible, we should be thinking, well, what's friction going to do? Friction takes away energy. So we should be thinking about that. Since friction is not negligible, it will, and we can think of how does it do, how does it take away energy? Well, through work. It will do negative work on the student, board, earth system, decreasing the total amount of mechanical energy in the system. Which means if I start out with some potential energy and some kinetic energy, and let's say I started out originally with 100 joules, friction's going to take away 100 of those joules, or not 100, but some of those 100 joules. And so if this quantity here was 100 before, but now friction is decreasing this amount, that means that when we're done stretching the spring will stretch such that it holds less energy than before. So the energy stored in the spring or in the cord, energy will be, I'm going to go ahead and say this elastic potential energy. At the end will be less, causing stretch length to be less. Let me know if you guys have any questions, but that's it for today. Those are the questions on the free response for Unit 4. We'll go ahead and stop recording here. Thank you all.